Hello everyone, this is going to be a review video for MA 200 Calculus 1. So what I'm going to do in this video, I'm planning to keep it kind of short and just kind of give you an outline of topics and sort of cover some of the highlights, just remind you of some things that you should be studying. Um, First of all, let me start by saying that the final exam, date and time, are in the syllabus. So that's posted and you can refer to that. I also am going to say that there's a review packet posted. Review packet and answer key. By the time you're seeing this video, the review packet and answer key are posted. Now, before I start kind of going on an outline of topics, I also want to remind you of some other things that you should study from. So also study from, when I say also, I mean in addition to the review packet. Anytime I give out a review packet, I'm always worried that students are going to look at it and not look at anything else. But you should also be studying from the notes that you've taken. You've been taking good notes all semester. Now's the time to use them. Review your notes. Go through, you could skim through some sections, and then when you get to the sections that you think are difficult, you should look at them a little closer. You can also study from the textbook. Again, especially from sections that you find difficult. You can study from old homework and tests. And you can study from old packets or worksheets that we've had. Just any practice problems that we've had throughout the semester. All right, so like I said, I'm planning to keep this a little on the short side. Basically, I feel like you have all of the practice problems that you need. So I'm not really planning to do any practice problems in this video. You've got the review packet, you've got older things to look at, and what I really just want to do is do a quick refresher on, what are the topics we've covered. And really, as far as like what sections are on the final exam, it's basically, you can look at the course schedule. Everything that we've covered is fair game to possibly be on the exam. Okay, so you could look at the course schedule and use it like a checklist. Look at each section and make sure you know what types of problems get asked in that section. And if you know how to answer problems from each section, then you should be set. So I'm just going to cover some of the highlights. So first of all, we started with chapter 1, which is limits. And I feel like what we've done this semester, I think that the three big topics that we've covered are limits, derivatives, and integrals. And, we've been doing integrals lately, so we don't want to lose sight of how the semester began, and it began with limits. We started with just learning how to evaluate them, evaluating limits, and remember that this is before we knew about L'Hopital's rule. So the way that we solved them we might need to do things from algebra, like factor or multiply by the conjugate. For limits involving the square roots, we sometimes would multiply by the conjugate over the conjugate. You can go back and review that. But yeah, basically, we were able to evaluate a lot of limits before we knew about L'Hopital's rule. And L'Hopital's rule, which I'll talk about a little later, L'Hopital's rule is not for every type of limit problem. It's really just for certain limits. Okay. We talked about one-sided limits. That would be a limit as x approaches a with a little plus sign, or a limit as x approaches a with a minus sign. You should know what that means. We talked about limits based on a graph. So instead of just limits where you're given some kind of expression and you're trying to evaluate it, there could also be things where you're given a graph and, maybe there are some questions about it. A lot of times those tend to be piecewise functions because those are pretty interesting. You should be able to know limits visually. What do they look like in a graph? We had a section on limits involving infinity. And that section discussed asymptotes, right? Because as x goes to infinity, or f of x goes to infinity, or negative infinity, we call those situations asymptotes. And we had a section in this chapter on continuity. So continuity is, basically the topic of whether or not a function is continuous. We talked about whether a function is continuous at a point, and also whether or not a function is continuous on an interval. And a lot of functions that show up in calculus are continuous for their entire domains, which is nice. Just as a little side note off here, I'm just going to say section 1.5 will not be on the exam. All right, so those are some of the highlights from Chapter 1. That brought us to Chapter 2, which was all about derivatives. And remember, originally we had the definition of the derivative, and it was based on a limit, and that's why we did it in this order. The definition of the derivative is the limit of the difference quotient. Here, I'll talk about that first, I guess. Definition of the derivative. Limit as h goes to 0, f of x plus h minus f of x, all of that over h. Now, we could say that that's the definition of the derivative, but I would also like you to understand, informally, what does the derivative mean? What does it tell us? You should know that it measures a rate of change, that we sometimes call it the instantaneous rate of change, and it's telling us what is happening to the function at that point. Is it increasing? Is it decreasing? We talked about slope of the tangent line. You should know how to find the slope of the tangent line based on a given function or given a graph. So if I gave you a graph and I asked you, what's the slope of the tangent line at x equals 2? You should be able to look at the graph, look at that part of the graph, and you should be able to estimate what the slope of the tangent line is there. That comes from just knowing what a tangent line means. Let's see. We also, pretty early in this chapter, we talked about the second derivative, f double prime. And something I just said out loud is rates of change. And this includes things like velocity and acceleration. You should know how they are related. Distance, velocity, and acceleration are all related to each other by derivatives. And we began, originally we began with calculating derivatives with the definition, with the actual difference quotient formula here. And then we started establishing a bunch of rules, a bunch of shortcuts, so that we knew how to do derivatives of first of all, polynomials, but then also things like the square root of x, things like 1 over x squared. I don't know why I chose 1 over x squared here, but just things like that. 1 over x. X raised to a power is basically the rule. And then we had rules for e to the x, a to the x, trig functions. Some of these got their own sections. ln x and log base a of x. Here, I'm going to show you some of these just to remind you. This one, a to the x ln a is the derivative of a to the x. This one, derivative of ln x is 1 over x, and this is 1 over x ln a, where a is a constant, so ln a is a constant. So we started off with all of those rules, and then we came up with 3 big rules: the product rule, the quotient rule, and the chain rule. And I always say that those are the 3 big derivative rules. If you're good at all 3 of those, then you can do a lot of problems. And I'm not going to recite the formulas right now, but you should know them. You should know the formulas for them. And you should know the chain rule is sort of it's a formula, but the chain rule is also kind of like a method of breaking down a function into like what is the inner function and what is the outer function. And we also had a section on implicit differentiation. So that's where you have an equation that's given that involves x's and y's. You want to find dy dx, so you do d dx of both sides. You simplify, you solve for dy dx. Usually that involves using the chain rule. Let's see, what else? Also in this chapter, I said you might need to know the slope of the tangent line. I guess one other thing I want to mention somewhere in here, this might not be necessarily in order, but should also be able to find the equation of the tangent line. I don't think I said that above. I mean, it kind of goes with finding the slope of it, right? But if you're given a function f of x and you're given a point, or even just an x value, you could find the slope of the tangent line by finding the derivative and putting in the x value that you were given. And then you know the slope and you know a point. And from algebra and pre-calc, you should be able to find the equation of the line since you already know the slope and a point. You could use point-slope form. Towards the end of this chapter, we had a couple of sections that that kind of blur the line between chapter 2 and chapter 3. There was a section on related rates. These were word problems about how 2 different rates of change are related to each other. And you should know some basic formulas, like the area of a circle, pi r squared. You should know circumference of a circle is 2 pi r, where r is the radius. Let's see. You should know area of a rectangle or triangle. Volume of a box. Pythagorean theorem could show up. You know, if you're talking about a related rates word problem that involves right triangles, Pythagorean theorem might show up. Or another thing is similar triangles. You know, how to work with similar triangles. So if there are any other formulas that are like a little bit more obscure, like the volume of a cone, what else? Volume of a sphere, I guess. I would give you some of those formulas if you needed them. I'd like you to know these ones. And then the last part, look at this, this is a pretty big chapter, isn't it? The last part of chapter 2 was linearization, which is also known as linear approximation. And that's basically where we use the tangent line to approximate a curve. It has a formula, y equals f of a plus f prime of a times x minus a. And you should know how to find this. You know, basically you'd be given f of x, so you would find f prime, and then you'd like put this all together. You should know how to find this, and you should also know how to use this if a problem tells you to use it to approximate something. So that was a big chapter. I guess that's probably the biggest chapter that we've had. But it's really important that you know how to calculate derivatives. You know, that you're very good at derivatives by the end of this course. Chapter 3 continued our discussion of derivatives, but it was applications of derivatives. And I guess this began with us talking about local maxima and minima. Let's see. Whether a function is increasing or decreasing. We also talked about absolute maxima, minima. I guess something that goes along with all of this is that we did these using sign charts and critical points, so you should know what those mean. You should know about concavity and inflection points. And you should know about putting this all together to draw the graph. So let's say you're given a function f of x. This would be a good type of problem to have multiple parts. Like it could say, you know, part A, where is the function increasing, where is it decreasing? Part B, where are the local maxima or local minima, if there are any? You know, part C, where is it concave upward and downward? Part D, what are the x-coordinates of inflection points? Part E, put this all together to draw the graph of the function. And you know, if you do that, if you want to like find all this stuff and then put it together to draw the graph, you might also want to find some additional points, such as the x-intercepts or the y-intercept, because they could help you make an accurate graph. And we did that in class, but another type of problem could be, instead of just asking you to draw a graph, I could also give you some graphs and ask you questions about them. You know, maybe I could say like, all right, which of the following is the correct graph for this function f of x? Or I could give you a graph and I could ask you what are the intervals on which it is increasing or decreasing. You should be able to tell that from a graph. Local maxima or minima, you should be able to tell that from a given graph. So there's a lot of different problems that could come up there. Maybe even just find the critical points. That could be a problem. All right, so in addition to that, chapter 3, you know, had a few sections that all went together on those topics, but there were some other things in chapter 3 as well. We had optimization word problems. So I feel like the two big word problem sections that we had this semester were related rates, which we talked about at the end of chapter 2, and optimization. So optimization includes things like find the best dimensions of something. That could be like the dimensions of a rectangular field, or a can in the shape of a cylinder, or anything like that. Sometimes you want to find the max area, or maybe the max profit, just etc. Anytime you're trying to find a maximum or a minimum in a word problem, that's what we call an optimization problem. And then towards the end of chapter 3, because it doesn't really fit in anywhere else, it is an application of derivatives, was L'Hopital's rule. Now, it feels like L'Hopital's rule should go with limits, which was chapter 1, but we couldn't do L'Hopital's rule in chapter 1 because we needed all those derivative rules. What I want to remind you about this is that you should only use this for indeterminate forms. Because there were some limits that we did back in chapter 1 that were just not indeterminate forms, This is for 0 over 0 or infinity over infinity forms. And then, let's see. The last chapter we talked about was chapter 4. I'm just going to say this was integration. Integrals, integration. We started off by talking about antiderivatives. Antiderivatives, and we wind up talking about the indefinite integral. So I guess I'll put that here. The indefinite integral of f of x dx. You should know that this means the family of all antiderivatives. So basically, answers to problems like this are usually a function of x with a plus c at the end. And it's all antiderivatives of lowercase f. We talked about estimating area using rectangles. And we tend to do problems that are maybe like 4 rectangles or 6 rectangles, maybe 8 at the most. And the functions tend to be relatively simple. But you should understand what is meant if I ask you to approximate an area under a curve using rectangles, and if I said to use rectangles with left endpoints, or if I said rectangles with right endpoints, you should know what that means. Or even if I said midpoints. In class, I think we called those L4, R4, M4, if it was 4 rectangles. Let's see, what else? We had sigma notation. So that's the uppercase Greek letter sigma, and it's used to be a way of writing long sums in a compact form. And then from here, we were able to start talking about definite integrals. And you should know that this gets you the exact area under the curve. So indefinite integral. We use a lot of the same rules, but they kind of represent different things. Indefinite integrals is getting us antiderivatives. Definite integrals getting us the area under the curve from a to b. How are the two related to each other? Well, by the fundamental theorem of calculus. So you should know the fundamental theorem of calculus and just kind of have an idea of what it means. Like, what is it really telling us? What does it say? I'm not going to ask you to prove the fundamental theorem of calculus. You know, I'm not really asking you to prove things. But you should have a broad idea of just what is it. And then some of the things that we talked about recently towards the end of the course, substitution rule. And the substitution rule can be used for indefinite integrals and for definite integrals. That's just to help us with some tougher integrals. Sometimes you have to use it. And we talked about area between curves. All right, so sometimes you have a curve up top and a curve on the bottom, and you want to know the area of the region between them. We talked about that, so you want to know how to do the area between curves. So this has been kind of an outline of everything. Yeah, 4 chapters. It's kind of interesting to see it all summed up on just 2 pages. But this was Calculus 1. Just, I guess this was the list of topics. A couple of things I'll say before I wrap up. One thing I want to say, since this is kind of the end of the semester, is, you know, I think some of you are planning to take Calculus 2. It just depends on what your major is, whether you're going to take Calc 2 or not. I just thought I would tell you that Calculus 2 picks up right where we left off. Okay, so every professor is different, but I'll tell you that when I teach Calculus 2, I use the same textbook, and I pick up exactly on the section where we left off. I actually spend the first day of Calculus 2 basically doing the same thing that we did in the last day of Calculus 1. Just like one day where we overlap, but then we continue talking about integration. Calculus 2 has a chapter on applications of integration, so it continues from here. What else can I say? As far as our final exam, I want to remind you to try to be well rested. You know, eat a meal before it. It's a long test. And what else can I say? Yeah, you know, try to be at your best. Try to be focused with no distractions. And I know everybody should be able to do this. So yeah, I will wish you good luck, and I will see you for the final. Feel free to message me if you have any questions.